Okay, so this is the first seminar of this year, and Daniel McGinnis from Iowa State will present something about discrete geometry, right? KKM, please.
All right. Yeah, thank you so much. For letting me give a talk here. It's definitely really cool. I watched like a bunch of these on YouTube, so it's kind of cool to be part of that as well. I'm going to be talking about applications of the KKM theorem to problems in discrete geometry. So especially if you like problems in discrete geometry, I think this might be a nice little tool to have in the back of your mind in case you're working on problems. This might be something that you could try that might help with any problems that you're working on. I'm going to give some motivation for why I think this is a good tool to have kind of in your back of your head if you're thinking about discrete geometry problems. And I'm going to say what the KKM theorem is, and then I'm going to give examples on some examples on which it was used to solve some problems. Okay, so first, the kind of problems to get into the kind of problems I'll be talking about. I'll talk about Helly's theorem, which kind of kick-started a lot of the problems I'm going to be talking about. So Helly's theorem says that if you have F, a family of compact convex sets in Rd, with this property that whenever you take d+1 sets of your family, that they have a common point. In other words, I mean the intersection of these d+1 sets will be non-empty. Then Helly's theorem says that this family F can be pierced by one point. So by pierced by one point, I mean there's a point in the intersection of all the sets in F. So in other words, again, the sets in F have a non-empty intersection. So the big theme in Helly's theorem is that we have a family of convex sets, and it satisfies this local condition. So the local condition here is that every d+1 sets have a non-empty intersection. And the Helly's theorem tells us that we can conclude then a global condition. The global condition being that the intersection of all the sets in the family have a common point. Okay, so that's the big theme here, is that when your family satisfies this local condition, when does that guarantee you a global conclusion? Okay, so just a little illustration for Helly's theorem. So here I have 3 convex sets in R2 that have a common intersection. And if I want to add another set to this family, while maintaining the local condition, so here D is 2, so we want every 3 sets to have a common point. So if I add another set and preserve this condition, this set needs to have a point in this pairwise intersection, this pairwise intersection, and this pairwise intersection. And then so Helly's theorem tells me that this convex set would have to also intersect the triplewise intersection. Okay, so that's just a little illustration of Helly's theorem in 2 dimensions. Okay, and so like I said, Helly's theorem kind of kicked off a lot of different directions, a lot of different lines of research in discrete geometry. And so there's a lot of variations of Helly's theorem that have motivated a lot of research and are still motivating exciting research to this day. So examples is changing the local condition. So the local condition in Helly's theorem is that every d+1 sets have a common intersection. Maybe if you change this local condition, weaken it or strengthen it, how does the conclusion change? There's variations of Helly's theorem to more general families of sets. So Helly's theorem is stated for families of convex sets. There's also theorems for families of disjoint unions of convex sets, or sets that aren't convex but maybe have nicer intersections. There's quantitative versions of Helly's theorem. So instead of just guaranteeing that the intersection of your family of sets is non-empty, what if you want your conclusion to be the intersection of the phi family sets has some volume? Then, so that's a quantitative version. So, yeah, if you want to guarantee that you have some volume in the intersections of your sets. And then there's colorful generalizations, and many more. So there's a lot of different variations. There's just a few of them. And one of them that I'm going to be talking about also is, so Helly's theorem is about intersecting your families with a point, and what if we want to intersect our family with a line or a plane or some higher dimensional f-concept space? So that's another one that I'll be talking about. Okay, so here's one of the more well-known kind of variants of Helly's theorem, where we alter the local condition for our family of sets. So, and basically this definition here is describing this local condition. Okay, so a family F is said to satisfy the PQ property if for every P sets in F, Q of them have a common point. Okay, so this is going to be like a different kind of local condition. So in Helly's theorem, we were our family of sets have the d plus 1 property. So whenever I take d plus 1 sets, all of them have a non-empty intersection. So that's kind of like the relation to Helly's theorem. So this is just a different kind of local property. And there was one open problem by Hadwiger and de Brunner in 1957 was basically an analog of Hadwiger's, Helly's theorem, which is instead of having the Helly condition, if you have this PQ property, can you guarantee some kind of piercing result? And so this problem was proven by Alon and Kleitman in 1992, and here's what they proved. So they proved so P and Q are at most d plus 1. So Q has to be at least d plus 1 here. Otherwise, there's the conclusion doesn't hold. There exists a constant. So D here is the dimension. PQ is referring to the PQ property, such that every finite family F of convex sets lying in RD that satisfy the PQ property can be pierced by this constant number of points. So this constant doesn't depend on your family, it only depends on these parameters D, the dimension we're living in, and P and Q, the local condition satisfied by the family of sets. So in particular, what Helly's theorem tells us is that when P and Q are d plus 1, so when you have the d plus 1 property, this constant is 1, because it's saying there's a point piercing the entire family. And what this theorem says is that, yeah, there's a constant number of points, but it may be more than 1. Okay, and this is this theorem and its proof has motivated like a lot of different directions in this kind of research, so it's considered like a very celebrated result. But one thing that their proof doesn't do, interestingly, is it doesn't find good bounds on these points, like finding the optimal number of points needed to pierce these families satisfying the PQ property. And so one possible area of interest is to determine what these points should be, or at least good bounds for what these constants should be. In the first non-trivial case in which these points aren't known is when D is 2, so when our family of sets are in R2, and when they satisfy the 4-3 property. So the constant C243 is not known. This is the first kind of non-trivial case for which this constant is not known. Because C233 is just Helly's theorem, so it's known. So the next one is C243. Okay, and so one of my contributions in this area was I proved this upper bound on C243. So this lower bound, this had already been known. It's kind of widely believed that this constant should be 3. And so my contribution was showing that this was at most 9. Okay, so why am I telling you this? It's because I used the KKM theorem in this result. So this is, part of me trying to convince you that this method might be useful to know.
What was the previous bound?
Oh yeah, the previous bound was 13, and that was from 2001 by Yarfash, Kleitman, and Toth. Okay.
And maybe it's worthwhile to say what is the Alon-Kleitman bound.
Oh yeah, so when Alon and Kleitman proved their theorem, they weren't worried about coming up with good bounds, and their bound was something like 343 or 243 or something like that. So, so yeah. I think this problem is really interesting personally. Yeah, I really like it, but it seems really hard to really get tight bounds on this kind of number.
So there is an award on improving this bound.
Oh.
So you'll get $10 for each unit improvement.
Yeah. So technically, I got a mail from Budapest for $40. And I never checked my math mailbox, and so they emailed me. They're like, "Did you ever get this?" Or I was like, "Oh." So I figured out like months later after they already sent it.
Who's
But
sending this money? It's not by Erdish, but someone else.
I think
Toth.
yeah,
Maybe
Geza
Geza.
sent it.
Uh-huh.
Yeah, but that was kind of funny.
They give a bigger reward for improving the lower bound, no?
Oh yeah, if you prove the lower bound, it's $30 per.
Per
So, yeah. All right. So, yeah, this is kind of the first. Okay, yeah, I should also say. So in this proof, I used the KKM theorem, and this was kind of the first place where the KKM theorem was used in this way. And at the time, I used it, but I didn't really see the significance of it at first. And then later, we kind of saw that we could use this method to prove more stuff. Okay. So now I'll be talking about line piercing. So as I talked about before, Helly's theorem deals with piercing families of sets with points. We can also ask similar questions when we would like to pierce families with lines, or even higher dimensional subspaces, but for now we'll just deal with lines. So the first question you might ask in this regard is if there are analogous statements for Helly's theorem for piercing families of sets with lines. So first I'll present sort of an analogous kind of local condition for lines instead of points. So we say that a family of sets F, and so for right now I'll just be focusing in R2. So yeah, well for lines we'll just focus in R2 for now. So we'll say a family of sets F and R2 has the TK property if every K sets in F can be pierced by a line. Okay, so this is very similar to the local condition in Helly's theorem, which said that every D plus 1 points is pierced by a point, but now we have, yeah, so TK is kind of like the analogous condition, but for line piercing. Okay, so yeah, I have an example here of, so here's 4 sets in R2. It has the T3 property, so you can kind of see that every 3 sets has a line piercing them, but it doesn't have the T4 property, because there's no line hitting all 4 of these squares. So in particular, there's not a Helly theorem, or there's not the direct analog of Helly's theorem doesn't work for lines, because every 3 boxes are hit by a line, but there isn't a line hitting all 4 of the boxes in this example. And in fact, Santelot showed in 1940 that for every K, there exists a family of convex sets in R2 with the TK property, but cannot be pierced by a line. So no matter how much you increase this local condition, you can't guarantee a line intersecting your family. And yeah, so there are known local conditions that guarantees that your family of sets can be pierced by a line. So this is called Hadwiger's theorem, but I won't be going into that in this. Okay, so for the positive results, Eckhoff in 1969, he showed that a finite family of convex sets with a T4 property can be pierced by two lines. So in particular, this result is best possible. This 2 can't be reduced to 1 by what Santolo showed. So at the point when Eckhoff was working on this, it was unclear if the T3 property even implied that there is some constant number of lines that can pierce your family. So at the time that he was working on this, that wasn't clear. Yeah, so that was the question at the time. What about families what about families with a T? Yeah.
Is it for RD or R2?
Oh, R2. Yeah. So yeah, for this portion, yeah, we'll be focusing on R2. Thanks. Yeah. So the question was, what about families with the T3 property? And so Eckhoff showed a lower bound here. He said that he's proved that there is a family of convex sets in R2 with the T3 property, but here it cannot be pierced by 2 lines. So it's different for families with the T3 property versus the R4 property. Also, I forgot to mention something here. If you have the T5 property, then you also have the T4 property. So this also gives you the best result for families with the TK property for k greater than or equal to 4. So that's why here T3 is the only case left at this point.
You say that so T4 implies T5?
Oh, sorry, T5 implies T4 property. Because every 5 can be pierced by a line, then that means every 4 can be pierced by a line in particular.
Because you choose same set twice? Is that the reason?
Oh yeah, well you take 4 sets and then just choose a 5th one. These 5 can be pierced by lines, so that means your original 4 could have been pierced by a line.
Okay.
Yeah, so in general, yeah, like TK plus 1 property implies you have the TK property. Okay, thank you for the question. Okay, so this is kind of a lower bound for Eckhoff. You need at least 3 lines for some families at least. For the upper bound, the first upper bound result was by Kramer in his PhD thesis in 1975. He showed that families of convex sets in R2 with the T3 property can be pierced by 5 lines. So he proved an upper bound here, but there's still a gap between what the correct number of lines should be. All right, and then Eckhoff, around 20 years later, he improved this by showing that families of convex sets in R2 with the T3 property can be pierced by 4 lines by slightly modifying Kramer's proof. So at this point, the question is, do you need 3 lines or 4 lines? And Eckhoff actually conjectured that 3 lines should be enough. And then finally, myself and my advisor Shira, we proved this conjecture of Eckhoff. So we proved that families with the T3 property can be pierced by 3 lines. So kind of settling that problem. And again, the reason I'm telling you this is because we use this method using the KKM theorem. So yeah, so here is this problem that, a very old problem, discrete geometry, and so this new kind of method was able to solve it in the end. Okay. So there's a couple of motivators for why this method might be useful in your own research as well. Okay, so now I'm going to talk about the KKM, or say what the KKM theorem is, and I will explain through examples how the KKM theorem can be used. Okay. So first, so here by delta n, this will mean the standard n-dimensional simplex. So this is just the convex hull of vectors EI. So EI is just this standard basis vectors, so it has a 1 in position I and 0 elsewhere. So yeah, so delta n, that will be the standard simplex, n-dimensional simplex. And So for the simplex, for every,
Oops. Maybe just cancel.
oh, yep. Yeah, so on the simplex, for every subset of n plus 1, so j here, there's a corresponding face that I'm denoting sigma j, which is just the convex hole of the EIs where an I come from j. So in particular, if j has two elements, if j is just a two-element set, then you're taking the convex hole of two vectors, and so that's like an edge of your simplex. If j is a singleton, that's the corresponding face is a vertex, and so on. So yeah, in particular, the vertices of the standard n-dimensional simplex, those are the standard basis vectors. So okay, and then so what the KKM theorem tells us. So it's a theorem about coverings of the simplex. So here I have these sets A1 to AN plus 1. So they're kind of corresponding to the vertices of the standard n-dimensional simplex. So the standard n-dimensional simplex has n plus 1 vertices, and so there's a set for each vertex. You can kind of think of it like that. So, and these are sets that are forming a sort of a cover of our standard n-dimensional simplex. So if you have this cover with this property that, so the face corresponding to j, so sigma j, is covered by the union of the AIs, where I come from j, then the intersection of the AIs is non-empty. So in particular, what this condition is telling us, so if j is a vertex, so say j is a singleton I, this is saying that EI has to be an element of AI, and so on. And say the edge between EI and EJ has to be covered by the union AI, AJ, and so on. And I'll show a picture of this later. But yeah, so one thing that might be interesting is actually the KKM theorem is an equivalent version of Brouwer's fixed point theorem.
Mm-hmm.
So it's actually not really some crazy thing we've never heard of. It's equivalent to a familiar kind of theorem. Okay, so let me just give a short demonstration of the KKM theorem. So so here I have the standard two-dimensional simplex. So here I've drawn it in the plane, but technically the standard two-dimensional simplex lies in R3, but that's okay here. So so here I have A1. So in the KKM theorem, I need E1 to be contained in A1. Here's my set A2. Again, I need E2 to be contained in A2, and also I need the edge from E1 to E2 to be contained in the union of A1 and A2. So here that condition is satisfied. And then here's my set A3. Again, I need, for the KKM theorem, I need E3 to be in A3, and so on. The edge from E1 to E3 has to be contained in the union of A1 and A2. And then finally, the whole simplex has to be the union of all the AIs.
So I forgot the AIs are open, or the AIs are closed.
Oh yeah, yeah. So the way that I stated it, the AIs are open. It's also true if the AIs are closed. Yeah. And here I kind of drew the AIs kind of nicely. They're like connected and all that, but in general they don't have to be. They just have to be open. Yeah. And so the conclusion of the KKM theorem is that we have this point in the intersection of all the AIs. So that's the KKM theorem. And so now I'm going to show some basic examples on how it could be used.
Why do they call it KKM?
Oh yes, thanks. It's named after the people who proved it. So it's
Knaster,
yeah, Knaster,
Kuratowski.
yeah, Kuratowski and Mazurkiewicz. Yeah, I'm probably pronouncing those wrong, but yeah. Okay, so here so what I'll do first to kind of illustrate a first example on how this theorem could be used, I will prove this theorem of Eckhoff, that a finite family of convex sets with the T4 property can be pierced by two lines. So this wasn't his original proof, but this is a different proof of his result. Okay. So what we're going to do is we're going to actually use the KKM theorem on delta 3, so the three-dimensional standard simplex. So a point in delta 3 has 4 entries, and these entries sum to 1. Because we're taking the convex whole of the standard basis vectors. Okay, and then here's what we do. So we have a finite family of convex sets. By like a simple, like little technical reason, we can assume that the convex sets are actually compact. So the union of, the whole family is contained in a bounded region. So we can go ahead and assume that all of our sets are lying in, say, the unit circle, like inside the unit, like in the unit disk, right? So all of our sets are lying in here. And what I do is I'll fix a point on the circle, and then I will describe how this point x in delta 3 will correspond to 2 lines and 4 regions. So here's what we do. So we start with this fixed point 1, 0, and we take the first entry of our point x, so x1, and we go around the circle by an x1 amount. So what I mean basically is that this length here from our fixed point to x1 is like an x1 proportion of the entire circle. So if the circle has perimeter 2 pi, then this one will be x1 times 2 pi. And then we do the same thing with the next point. So we start at x1, and now we go x2 over. So this whole so from the fixed point to the second point, this arc length will be x1 plus x2 proportion of the entire length. And then for the third point, we again we do the same thing. We start at this point, and we go kind of x3 over. And then since x1 plus x2 plus x3 plus x4 is equal to 1, when we add x4 again, we come back to our starting point. So we don't get a new point by adding x4 then. Okay, so this is kind of like our first step. We define these four points on the circle. One of them is fixed. And then now we make 2 lines by just connecting the dots. So I take the first fixed point, I connect it to the second one, then I connect the other 2. So I get 2 lines here. So this is how a point in delta 3 corresponds to 2 lines. Actually, you may notice that technically it's not giving you all possible pairs of lines. For instance, in this construction, the 2 lines will always intersect. So this point will never parameterize 2 non-intersecting lines. And now you can see here we kind of have 4 regions. So I'll call this region kind of in between our fixed point and x1. This will be r1. The next one will be r2x, r3x, and r4x. Okay. And yeah, and one kind of nice property here is that if one of the entries here is 0, then the corresponding region is empty. So for example, if x1 is 0, then this first point actually corresponds with 1, 0 here, and r1 of x will be empty. So this kind of property will be basically will end up guaranteeing that the family of sets that I'll end up defining will be a KKM filter. So we'll get to that in a second. Okay, so let me define how to actually define the KKM sets. Okay, so basically how you define it is you put a point x of delta 3 in AI if and only if there is a set of the family contained in the ith region. Okay, so in this example here, the point x would be in A2 because we have a set in the in the region R2x. Okay, so the KKM sets are kind of corresponding to the regions. If you have a set in that region, then that point will go into that corresponding set. And there's some like small details that are kind of easy to check, but if you assume that the family is not pierced by two lines, so here's kind of like a contradiction proof. Then what happens is for every such configuration of lines, your family is not pierced by these two lines, so that means some set has to be in a region. So basically this is saying that our sets AI are covering your simplex. So there's a little bit to be checked there, but it turns out that if you assume that the family is not pierced by two lines, then you'll get a KKM cover. And so what does the KKM theorem tell us? What is the conclusion? Well, it tells us that, so there's a point of delta 3 in the intersection of all the AIs. So what that means is for each region, for this point in delta 3 and the corresponding regions, I have a set in each region, right? Because X is in A1, that means I have a set in the first region. X is in A2, that means I have a set in the second region, and so on. And so now you can see that this is, well, yeah, so this gives us actually our contradiction. This completes the proof. The reason is because, well, we assumed that our family of sets had the T4 property, if you remember. But there's no line that can intersect the interior of these four regions. So there is no line that intersects all four of these sets. Okay, so that's the contradiction that we get. So we assumed that we couldn't pierce with two lines. That meant we get a configuration of 4 points, 4 sets like this, and that violates the T4 property. Okay, so that would complete the proof there. Okay.
What if one coordinate is 0, then?
Yeah, so you can't, so the fact that X is in the intersection of the AIs means that the coordinate won't be 0, because we have to have a set in that region. So it couldn't be that, yeah. So it couldn't be that X1 is 0, otherwise this region would be empty and you wouldn't have a set there. Yeah.
Where do we use the sets are convex?
Oh, good point. Actually, you don't need that they're convex. You only need that they're connected. The reason is a line intersects a connected set if and only if it intersects its convex set.
In R2.
So, in R2. So, yeah, so you can just replace the sets with the convex holes and it's the same equivalent problem. Yeah, good point, thanks. Okay, and actually, there's actually another way to do this too. So what Eckhoff proved originally actually is that, oh, well, I'll mention first. So notice that we proved something a little bit stronger. Not only did we prove that there are two lines piercing the family, but there are two lines piercing the family where one of them contains this fixed point that we have. So we kind of have like this extra.
And also they intersect.
Yeah, and they intersect, yeah. So we kind of have like this extra condition on the lines. And actually what Eckhoff originally proved is he proved that there are two lines intersecting the family and you can fix one of the directions of the line. And actually you can prove this using the same kind of method. So I'll just kind of like briefly describe how to do that. So now I'm not gonna fix a point on the circle. What I'll do is I'll fix a direction. So I'll just fix the direction, which is just a vertical line. So I'm gonna find, yeah, two lines that pierce my family, and one of the lines is vertical. So basically what I do is I take a point in delta 3. So I have x1, x2, x3, x4. And so what I'll do is x1 and x2 will tell me how far I'm going to slide over the vertical line to the left, starting from all the way on the right. So x1 and x2 kind of tell me how far to the left I'm sliding this vertical line. So this goes over x1 plus x2. Again, it's like it's x1 plus x2 proportion of the total.
If they're both 0.
Sorry?
What if they're both zero?
Oh, if they're both 0, then it'll be this line, the one tangent. So that's how you get the first line, and so this would be x3 plus x4. And now to define the other line, what I'll do is kind of an arbitrary choice, but I'll start, say, at the intersection of this line with the circle on the bottom, say the bottom point. And what I'll do is I'll go over x1, and I have to kind of normalize it a little bit over x1 plus x2. And that's how I'll get a point here. Okay, so you might ask, oh, what if x1 plus x2 is 0 again? We're dividing by 0. But in that case, my line is already all the way on the right, and there's only one possible point you could choose. Okay, so that's just a little technical thing, but this is how it kind of works in the general case. So I'll go over x1 plus x2 here. Whoops, sorry. And on this side, I'll go over x3 over x3 plus x4. And then what I'll do is I'll connect. Maybe I'll withdraw this a little. And then what I'll do is I'll connect these points. So yeah, and then you can see if x1 was 0, then this region would have been empty because this point would have coincided with this point. Similarly, if x2 was 0, this region would have been empty, and so on. So you can define regions in almost the exact same way, use the KKM theorem, and so on. So yeah, there's a bunch of different ways that you can kind of play around with this kind of idea. Okay. Now, what about the T3 result that I told you about earlier? So if you have the T3 property, then you can be pierced by 3 lines. So it's a very similar proof, except now I'm going to use the KKM theorem in delta 5. And what I'll do is, instead of defining 4 points on a circle, I'll define 6 points on a circle. So again, I'll have this fixed point, and I define the 6 points in basically the exact same way. The only difference is that I have more points. And I connect points in a similar way too. So you're kind of connecting a point with like its opposite. And then here the regions are defined similarly. So here it'll be defined, so the region R1 will be defined as this wedge between x1 and 1, 0. So it'll be like this wedge here. R2 will be this wedge here. R3 will be this wedge here. So in particular, some of the regions are not disjoint, so some of the regions will intersect, but that's okay. And if we run through the same KKM argument, basically what we get, so we'll get sets in these regions. We'll also get sets in the other regions, but they're not really relevant. Already these 3 sets here give us a contradiction. So in any of this configuration of lines, there are going to be 3 pairwise non-intersecting regions, and you can see that there's no line that could pierce all 3 of them. So that's kind of how we get our contradiction here. If you assume your family can't be pierced by 3 lines, then you're contradicting. Then your family couldn't have the T3 property. Yeah.
What if the triangle has been flipped?
If it's flipped, yeah, then you'll use the other 3 regions. So here it's R2, R4, R6. If it's flipped, then it would be R1, R3, R5.
What if they have a common point?
If it's a common point, then it's the same thing, except now you'll have a contradiction for both R1, R3, R5, and R2, R4, R6. So yeah, if this triangle was a point, then these 3 sets still wouldn't have a common line. through them. Yeah. But yeah, it's again, it's kind of interesting that this way that we parameterize lines, you don't get every possible choice of 3 lines. Again, for instance, this will never produce 2 lines that are that don't intersect. Okay, so I think the reason why this, there are more general ways to parameterize 3 lines in the plane. But then what happens is sort of like the topology of these spaces is kind of more complicated, and I think because we're kind of restricting which lines we're taking, it kind of simplifies our space into a simplex, and that's kind of why this works and helps us actually prove things. Okay, so I'll just do some more examples. So examples with more lines. So say we have now delta 7 and we have, so now we'll have 8 points along our circle. I just named them slightly different because it would have gotten too long. And now we have 4 lines instead of 3 lines. So we could do the same thing, define our regions in the same way. But actually, for some applications of whatever problem you're working on, you may need to define the regions slightly differently. So I'll give an example of how we might define the regions a little bit differently. So what I'll do here is, okay, well let me say something first. So what I'll do here is I'll define the regions sort of iteratively. So the first region will be the same, it'll be this wedge. And then for the next regions thereon, the region will be the wedge minus any points that came in a previous region. So this way you'll get disjoint regions. And so for this example, what ends up happening is you'll get something like this. So for example, this region originally was this wedge that came all the way down here and then here, but we took out the points that came in previous wedges, so now it looks like this. So now we parameterize these lines and we have disjoint regions. Okay, and then so this can be used to prove the following statement. So it can be used to prove this following measure partitioning kind of result. So let's say we have a measure mu. It's an absolutely continuous probability measure on R2. Okay, so absolutely continuous, that's just some technical thing. It just means that the measure of any line is 0. So we don't run into any issues there. And probability measure, that just means the measure of whole R2 is just 1. And we can prove that if you give me any 8 positive numbers that sum to 1, there exists a partition of R2 into convex regions, R1 to R8, such that the measure of the ith region will be alpha I for all I. And how we do this, we can just use the KKM theorem. So we kind of use this parameterization. So for a point in delta 7, I can form these 8 regions. And then here's how we define the AIs. So we simply just define AI to be the set of points x in delta 7, such that the measure of the ith region is at least alpha I. And so
Shouldn't you have that the mu I of R is greater or equal to alpha? In the theorem.
Oh, no, because, yeah.
It's a partition.
But the mu I's are different, no?
No, that's just one mu.
Oh, one measure.
Oh, yeah, sorry, yeah, it's just mu.
Oh,
one
sorry.
mu. Yeah, so basically,
Sorry.
okay, no, you're good.
No, I forgot that you didn't talk about other things.
Oh, yeah. Oh, yeah.
Is number 8 is included in here?
Sorry?
Number 8 is included in here.
Number
that-
8 is...
I mean, This theorem can be applied to other.
Oh yeah, sorry, yeah, yeah, 8 wasn't special here just because I showed in the previous example that there's 8. But yeah, you could do it for more numbers than just 8.
So is 8 best possible? Can you reduce the number? Or?
You can do it for any. Sorry, maybe this was me misleading. You could do it for 6. You could do it for 4. Yeah, I just said 8 because it was coming back to this example. So
I see,
it's
I see.
8's not special here. Yeah, that's my mistake. Yeah, it was just kind of demonstrating that this method could also be used for like measure partitioning results. Yeah, so if you define the AIs this way, you can. It's kind of like an easy check to show that it's a KKM cover, and when we get a point in the intersection of the AIs, that means for all I, mu I of Ri is greater than or equal to alpha I, but because it's a probability measure and these alpha I sum to 1, it actually has to be equal. Mu I of Ri will have to be equal to alpha I. So that's just kind of like small little details, but yeah, it turns out. Yep.
Can you use more than one measure?
Sort of. So, yeah, sort of.
Sort of.
Yeah, if you had say 8 measures,
8 measures.
then you could prove that mu I think. Wait, yeah, like for example, you could prove that mu I of Ri is at least alpha 1 for all I, but not equal. I think. And I think that's what you were saying earlier.
Yes. But for this theorem, is this argument true that if I have like one line and move around parallelly, so as soon as I hit alpha I cut, alpha 1 I cut, and then
Yeah, this is the one dimension. So you can think of it as a cake, a round cake partitioning third division problem.
Like
and if you take, so there is this one-dimensional cake that you can partition in the same way, and you use the KKM as well.
Yeah, that's a good point. That also works. So, yeah, this is it's not like the most interesting theorem, but the point is that you can use it for like these measure partitioning. Yeah, I just wanted a simple example to kind of demonstrate that. Okay. Okay, so here's another result by Shira that she proved using this, basically this same kind of idea where you define the regions to be disjoint in that way. She proved that a finite family of convex sets in R2 with the P2 property, so this means that whenever I have P sets, some 2 of them intersect. You can also think of this as this family has matching number P minus 1. Because if you take P sets and some 2 of them intersect. Yeah. Or matching number at most P minus 1, I should say. So if you have a finite family of convex sets with that property, then it can be pierced by roughly P over 2 lines. Yeah. So it's sort of like if you have a family with a P2 property, it can be pierced by as many lines as you would need for, say, just like a P element point set in generic position. And here's a problem is asking basically if this theorem is true in higher dimensions. So is it true that if you have a finite family of convex sets in RD with, again, this P2 property, can it be pierced by roughly P over D points? Maybe you need some constant like +1 or +2. Yeah. So basically, there's a 2 in the denominator here because if you have any 2 sets, you can be pierced by a line. And there's a D in the denominator here because if you have any D sets in RD, you can be pierced by a hyperplane. Okay, but I think the biggest kind of related problem here is if this method can be generalized to higher dimensions. So everything that I showed was in 2 dimensions, For example, is it possible to parameterize three planes in R3 using, say, like delta 8, or because you would have generically 8 regions. If you could do this, you would automatically solve a bunch of hard problems, basically. Measure partitioning results, piercing problems, etc. But yeah, so this I think is kind of the most interesting way to kind of push this method forward, if you could. Okay. And then you could basically extend everything that I talked about, but in higher dimensions, basically. So you'd get, basically by doing this one thing, you'd get tons of theorems for free, basically. Okay, and yeah, that's what I'll leave off on here. And thank you so much for listening to my talk.
Thank you. Any questions?
Can you fix the direction of one eye for the T3?
Oh yeah, that's a good point. I forgot to mention that. Yeah, you could do the same trick for the T3, T3 families.
So KKM, you said it's equivalent to Brower's fixed point theorem, which will be also equivalent to spanners and all these things. So I wonder whether you thought about like proving same thing by using this equivalent theorem.
Yeah.
Whether you might have a better formulation or easier.
I see what you mean. So see, like using Sperner's lemma or whatever.
For instance,
yeah. Yeah. I don't think I've tried that, but it could be interesting.
There's a similar version of Percival theorem, equivalent version of Percival theorem. I just wondered whether you thought about using that version for this kind of problems in discrete geometry.
Which version are you talking about?
So instead of Brouwer fixed point theorem, there's a like similar version of KKM theorem, the corresponding version of Percival theorem, equivalent to Percival theorem.
Sorry,
like a correspondence between KKM and the Brouwer fixed point. There is some analog
equivalent version of Percival theorem.
Okay, yeah, like KKMS theorem.
This is like a loose tonic.
Some close that covered or is it covered?
Yeah, it's similar version of set covering.
I see what you're talking about. And what was the question? I
just wondered whether it could be also used to prove.
Yeah, that's a good point. That's a good point. I haven't found anything like that, but yeah, I think that's an interesting thing to keep in mind. So you mean the set covering version of Borsig-Ulam theorem?
Yes.
Right. Okay, yeah. Sorry.
Any other questions?
How about the colorful version of
Colorful version of KKM? Yeah, so ideally you would want to prove that if you have, say, a red set, a blue set, and a green set, and if you take a red, blue, and red family, green family, blue family, and if you take a red set, green set, blue set, for any choice you have a line, then one of the families would have three lines piercing them. We actually weren't able to prove that. Well, we proved that that's true if you have instead 6 colors instead of 3 colors. So that's actually an open problem. So yeah, that's a really great question. Is if you have 3 colors, if you can prove the colorful version.
So in general, there is a colorful version of KKM theorem. So every time you use KKM, you can take out the KKM out as a black box and put inside instead the colorful KKM, and you will get some colorful version of any result that you put. And there are other generalizations of KKM, polytopic more sets than vertices, sets that corresponds to other faces as well, and each one of them will give some result. So yeah.
Yeah, that's a good point. Like in particular, if you're interested in trying to find this like higher dimensional analog, maybe these other kind of KKM theorems, like KKMS theorem, would be useful. So.
Yeah. So if the configuration space of whatever you try to parameterize is not necessarily a simplex, but you can find something more complicated, then maybe some polytopic version of KKM would be applicable.
Okay. Any other questions? Okay, if not, let's thank you.